This is the Early AI podcast hosted by Seth Earley. Join us as we delve deep into the passions, expertise, and experiences of thought leaders and practitioners to talk about what's possible with artificial intelligence. The Early AI podcast is sponsored by Early Information Science, your digital transformation journey with design and deployment of innovative technology solutions, as well as Vector. Now enjoy the show.
Well, thank you for joining us and welcome to today's Early AI podcast. I'm your host, Seth Earley, and each episode we're going to explore how artificial intelligence and data are shaping business and strategy and operations. Today, we're going to look under the hood of AI to look at one of the most overlooked constraints on AI advancement, and that is memory. Joining me today is Stephen Wu. He's a fellow and distinguished inventor at Rambus Labs. Stephen has been with Rambus for over 30 years and began his career studying neural networks. He brings a rare long view perspective on how memory technology shapes the limits of what AI can do. Stephen, welcome to the show.
Thank you very much, Seth. I'm really happy to be here.
So let's start off with some common misconceptions. I like to always ask our guests, what are the biggest misconceptions that business and technology leaders have about AI infrastructure and the role specifically that memory plays in it?
Yeah, it's a great question. So I think, really for decades, we've watched the industry make incredible advances in how fast processors can run and how fast they can do their computations. But really, the thing that's been going on behind the scenes is that memory has to keep up. These fast processing engines, they need data and they need it at higher and higher speeds in order to process more quickly. Probably the most interesting thing that we're seeing right now, AI is exacerbating this, but even on the regular compute side, is that memory has become a big bottleneck. And in many cases in AI, your speed at which you can actually process your AI information, create new large language models, things like that, it's really gated by the speed and availability of memory.
So that's really interesting. And so people aren't quite aware of the role. What is the conception? What is the misconception? Is it just that, hey, they're part of the infrastructure, nothing I can do about it? Or is it's behind the scenes, I don't care about it? I mean, what is your perspective on that?
Yeah, it's really interesting.
Kind of so what for people, right? So it's this bottleneck, but what are they thinking about it, or are they even thinking about it?
Yeah, I think, you get the whole range. I think there are people who are beginning to understand just how important and how critical memory is right now. And so I'll give you an example is basically the way, these AI engines, these GPUs have been progressing. We read about it all the time. These great companies like, NVIDIA and AMD, and even some of the big hyperscale people like Google and others, they produce these very fast chips that process our AI information very quickly. But kind of what's been going on behind the scenes is that memory has been doing its very best to keep up. Remember, these models and things, they rely on a lot of data. Now, what's more interesting is that over the last few decades, the speed at which processors have been improving has been faster than the speed at which memory's been improving. And you can see, if you just look at them relative to each other, then the memory is falling behind the rate of progress of the processors. And what that has been doing is has been gradually producing this bottleneck. And we see that bottleneck more than ever today, and it's getting worse going into the future.
When people think about that, they do think of it in terms of compute power. And we're saying compute power is constrained by memory. How should that change how organizations think about their AI investments?
Yeah, it's a great question. So
kind of like what do they do with that information, right? Okay.
Yeah. What's really interesting now is that you see more companies, they're understanding that they are limited by the amount of memory that they can get a hold of. Companies and big infrastructure players, they're signing long-term deals to lock up supply of memory to make sure it'll be there in the future when they need it.
So we were talking about that constraint and what do organizations do about it. And you were talking about the fact that they're buying up long-term supply, they're buying up long-term capacity, just as they are with power and just and other constraints and chips, right?
Yeah, that's right. And so like any other vital resource, what the companies are doing now is they're signing long-term supply agreements, and they're making sure that one of the most vital components that matters to them is going to be available. And in that case, it's memory. Now, this is true of other things, like you've mentioned. Power is another one, where there are long-term deals being signed, and even semiconductor manufacturing capacity as well. So people are looking very far out, and much further than I'm used to seeing in the industry.
Interesting. And so when you think about moving data between chips, that's something you talked about consuming the most power in an AI system. It's not the actual compute.
That's
It's the
right.
movement of that data, which was very surprising to me, right? Because
Yeah.
everybody talks about compute and compute power and compute in terms of gigawatts of compute, right? But you're saying it's really gigawatts of memory, right? What I don't know what the if you can give me the percentage of what that looks like of the power consumption. But why is it so difficult to solve, and what is the industry doing about it?
Yeah. So you really fundamentally, what you need to do is you need to move data to your processor and back from it, the results that come off of it. And it turns out that the amount of energy we spend is related to just the distance the data has to move. Now, it may not seem like much. You're talking going on the order of maybe 10 to 20 millimeters, but that's enough to cause, if you look at all the power that's spent on these high-end processors, more than 50% of the power is spent in circuits just trying to move data on and off the processor.
Oh,
So, it's pretty astounding. Now, when
yeah.
on the chip, we're talking very small distances. We're talking about, a few millimeters. But when you start to go off the chip and you're starting to go 10, 20 millimeters, or in some cases meters, if you have to go very far between chassis, that's where you spend all your energy. And so it's really astounding to think that as these companies are thinking through how much power they need to use, a lot of it is really related to simply moving the data back and forth.
And so, it's a constraint of physics, right? It's a
That's right.
constraint of materials. And is there something that what is it? And you also said it's very difficult to keep up with that performance, but what are some things that organizations are doing or the industry is doing? So what is on the horizon, or how are these problems being addressed at the fundamental level?
Yeah, it's a great
You got
question.
to
So
change physics. You got to change physics.
that's right. And it's exactly that. So you look at the problems and you realize, okay, the problem is a physics problem. So for one thing, it's distance. And so people are putting components closer together as best they can. Now, when we put these components side by side, I talked about maybe needing to go 10, 20 millimeters or even meters. What people are talking about now is stacking the components on top of each other. What that'll do is it'll cut down the distances by 1 to 2 orders of magnitude. So
Wow.
we're talking about much, much shorter distances.
Right.
But
And now there's energy savings from that, but then there's also energy dissipation problems. I'm
that's
sorry
right.
to cut you off, but
Oh,
yeah.
you hit the nail on the head right there. So, it sounds great when I say it that way, that all you need to do is stack these components. But there's two big problems. One is I'm now dissipating all my power in a smaller volume. So it makes it harder to cool. The other problem is it makes it harder to supply the power to everything that's there. So we've got these two problems, and the question is, what should the industry do about those? And there's a lot of active work right now on that particular area. Now, there are other areas where, when we're talking about going long distances, for example, if you're going between chassis in a rack or between racks in a data center, optics has long been viewed as the right technology to use. It is incredible at distance in terms of its data rate and in terms of its signal quality.
Easier to move photons than electrons.
That's right. Now, it is a big enabling problem, though, because, optics and photonics, they do exist for long distances, but for the distances people are talking about, it keeps getting shorter and shorter. And so now it becomes a tougher challenge to do things like to integrate it directly into the silicon and to integrate it directly into these silicon packages. So a lot of enabling work is going on in the industry right now to move interconnects, especially the ones that go over distance, to be all optical.
Gotcha. Interesting. So we talked a little bit about, and we've kind of hit on this, but you described the idea of memory tiering, where different data lives at different levels of proximity based on priority or usage or importance, right? What
That's
are
right.
the trade-offs, and
Yeah.
what do technology leaders need to think about when they're provisioning AI infrastructure?
Yeah, it's a great question. So you really need to think about how you want to support your users. So I'll give you an example. If you look at these LLMs and you have like a nice long conversation with your LLM, what you're doing is you're building up a context on that whole conversation. And really the broader context can't really all fit directly in the memory that's attached to the processor. So what you need to do is you need to take pieces of that and keep it close by, and pieces of it have to be a little bit further away. A really good analogy is if you think about storage in your house, you've got closets and you've got drawers and things readily accessible. But it's really not enough for most people. So you need to store some things in the garage. And you don't really like going in your garage. So you try and go in there as little as possible. And then if you have a lot of stuff, you might actually rent, like self-storage that's, a couple miles away. And you really don't want to go there very often either. And so the trade-off is really all about, kind of how recently and how frequently you've used something. You want that to be close by. And for the things which can, you can use less frequently and all that, they can be a little bit further away.
And so it's very interesting to kind of think about how they do that. Are these the problems for the data engineers? Are these the problems for the hardware engineers? Are these the problems for people procuring a compute capacity? Are these the problems for the hyperscaler? Who owns this problem? And again, what does a leader do? Sorry.
Yeah, I mean, it's really a problem for everybody. And, if you take a look, first of all, at the hyperscalers, are both procuring the hardware, but they're also writing a lot of the algorithms that are moving the data. And so if you think of it as a whole system problem, you think about it a lot as, what is my hardware capable of doing? How can I change my algorithms so that I can get better kind of locality and less movement of the data? And you think also a lot about working with the industry to enable what it is you need. And so we work with really lots of different companies that consume the technologies to try and understand what it is they need going forward. And there's a lot of really brilliant software people that work very hard to try and figure out, how do I get the most out of what I'm actually given today?
When people talk about context windows, and of course, the bigger the context window, the more easily you can, understand the nature of the problem and the details of the problem and the ancillary details of the problem, right? And I know I'm always running into, this conversation is too long. Like, you can't keep this anymore, right?
Yep.
And are those strictly memory problems? I mean, is that really what the limiting the limiter is?
Yeah, I mean, it's primarily around the amount of information that you're storing about that conversation and how quickly you can look it all up. And so it's really a storage and retrieval problem. You're trying to put some of that in memory. You're trying to put some of it in maybe further away kind of memory or storage, but it's a lot to search through. And especially if you've got this long context conversation, it just becomes a harder and harder problem as the size of the context grows. I mean, it's an important problem because we all want the longer contexts, right? But it's something where the industry, that's one of the things driving the industry's emphasis on improving capacity and bandwidth, the ability to move data back and forth, as well as the energy efficiency.
So when you think about training, and a lot of people focus on training.
Yeah.
But training of the new models and the frontier models and advancing those models is where the industry is trying to push the envelope and get better performance and better results and greater capabilities. But then there's also inference, which is the actual running of the model and solving those problems, right? And that's where you get into and I guess the question is, what are the differences in terms of memory requirements and in terms of how organizations architect their systems, whether they're doing training, building the models versus inference using the models?
Yeah, training has been this really interesting area unto itself. And basically what people have done is, years ago, they exceeded the capacity of just one GPU to really train these big models. And so now it's all about ganging together lots of GPUs. Tens of thousands of GPUs are all being used, for example, to train some of the largest state-of-the-art LLMs, things like that. So it's an enormous amount of compute capacity, enormous amount of aggregate memory, and lots of fast, high-speed interconnects that go back and forth. And what we've seen, from some of the hyperscalers and some of these really large, LLMs and things, really cost is no object. I mean, they're willing to spend pretty much anything to try and get the compute performance. But when you talk about inference cuts across lots of different markets. You can do inference in the data center, for example. You can do it in like home computers and things like that. You can do it in the office. You can also do it on your phone. And so the wide range of places that we want to do inference, what we look at there is we look at what is the hardware really capable of, and we try and make models and pare them down to have enough functionality that they'll perform well on the device that you've actually got. Now, sometimes what that means is I have to get that device to interact with something maybe a little further away. So I think we're all, kind of familiar with navigation apps where you've got something on your phone, which is telling you your position and, kind of what's around you locally. But if you're talking about plotting the further path away from you, then we might have to interact with a data center. And we try and do that occasionally. We try and do as much as we can locally. The same is true with inference. We're trying to do as much as you can locally, but sometimes you will need to go off that device to try and get other resources that you need. So in terms of, say, memory and things like that, I mean, your phone, it's got what's called low power DDR. It's a special kind of memory that it works really well with battery operated devices. You're talking about your home computer, for example, that's wall plugged typically. And so the kind of memory that you have in there is DDR memory, which is it's a big, common, very high volume kind of memory. And when you get in the data center, you have all kinds of things. There's DDR, like I just mentioned, that's kind of the workhorse memory for servers. We have a kind of memory called graphics DDR that originally was developed for graphics cards, but many graphics cards are used in AI. And at the very high end, you have something called high bandwidth memory, HBM. It's the premier memory, by far the highest capacity, by far the highest bandwidth, but it's also the most expensive. It's a little bit harder to design with. So you get a little bit of everything. And really, for the people that are consuming the memories, especially like a data center customer, they have to think a lot about, well, what are the different workloads they're trying to support and how much of each kind of memory do they need to buy to really support all the users that they have across the spectrum?
And so when you think about the innovation path forward for memory technology, what should leaders expect over the next 5 or 10 years? I know that's a long time horizon. It's hard to know what to expect in the next 5 months versus 5 years, but you have to have much longer planning and research and development horizon in any case, right?
That's right.
Yeah. So talk a little bit about what that life cycle is and where we are in the innovation curve, and then what's kind of exciting for Dell.
Well, so the thing I would say is, if you look historically, and this is up through about 5 to 7 years ago, the memory industry gave pretty reliable improvements in capacity and performance and power efficiency. And by reliable, it kind of depends on which memory you're talking about. But for example, DDR memory, which is the high volume memory, about every 5 years, we were able to double the bandwidth, and we were also able to double or quadruple the capacity. So you could kind of count on that. About every 5 years, you get 2 to 4 times the capacity and about double the bandwidth. With these high performance applications like AI, they're really driving these new kinds of memories like HBM and GDDR. And in the case of HBM, it's pretty shocking. About every couple of years, so much faster than DDR, about every couple of years, we're doubling the bandwidth and about doubling the capacity. So you can see it's really put the pedal to the metal on the memory industry. We have, we really are trying to keep up with that kind of cadence where doubling every couple of years in terms of the bandwidth and capacity. So it's really hard and really pushing the limits of technology. But I'll say there are a lot of clever people and a lot of really interesting techniques people are using these days.
And of course, with all of that, it requires much higher cost. So there's always the cost and performance trade-offs. How does that impact kind of the planning process, the budgeting process, the procurement process? Again, I want to kind of understand what that takeaway is for organizations when they're doing these things. How do they need to think about provisioning, planning, budgeting, forecasting, all of those elements?
Yeah, it's really hard to predict. And so I'll give you a couple of examples. So again, this kind of example I cited up to about 7 to 10 years ago, where we were doubling the memory capacity and doubling the bandwidth every about 5 years. What was pretty true was that was at a pretty constant price to the end consumer. And that's great, right? So the semiconductor industry has always been great at improving the capacity and performance while keeping the price for the whole component roughly the same. What's happened now is there's a kind of a complex set of interactions. So first is we are going at a much faster cadence now, which means we have to even develop the manufacturing capability much faster than we used to in the past. And that kind of thing is sometimes hard to fully recover the costs if the time frame is much shorter now. And so we've seen prices rise. In fact, over the last, I'd say, year, we've seen memory prices rise pretty dramatically. I was buying some just memory for my home PC, and
Hmm.
I did it over the summer. And I looked recently, that same memory I bought is 3 times the price now
Really?
at
Wow.
online retailers. It's
Wow.
but that in that particular case, it's really about shortages and a mismatch
Right.
of supply and demand. So I think what you see is you do see end users, like we talked about earlier, they're signing long-term commitments to really lock in prices. So at
Hmm.
least they have something that they know, right? They can plan
Yeah.
for. So, that's probably one of the interesting things that's going on in our industry right
Hmm.
now is the supply-demand imbalance is causing
Right.
this other kind of dynamic where you have to really think through how you're going to deal with, trying to get, relatively known prices for long periods of time.
So it's interesting in that, again, I'm not someone who knows about provisioning infrastructure and data centers and compute on a large scale. For a corporate decision maker, do they really need to think about, I mean, is this more of the in the weeds plumbing that it gets rolled into a plan and capacity again, or is it something that actually gets deconstructed? Or it's part of the contract that you need to look at, or it's
Mm.
part of the service level agreements. Is it hidden away somewhere? Is it locked away somewhere? Or is it something that has more visibility or will have more visibility, right? So in other words, how important is it to be aware of these
Yeah.
constraints and these bottlenecks and the provisioning and the supply, the supply chain and the changing capacity? How important is
Mhm.
it to have awareness and visibility to that? Because it all seems
Yeah.
to be, in my mind, again, I look at it a little bit more monolithically. You're buying, time or compute power or, or tokens or things like that, right? But how much does it become something that people need to actively be aware of and manage or identify risks of?
Yeah, it's a great question. So if you look back about maybe 10 years ago and you look at these large data centers where you could rent infrastructure, right? There were all different kinds and sizes of virtual machines that you could rent. And, some of them would give you, say, 2 GB of DRAM memory. Some would give you four. And it just depended on how much you wanted to spend. Well, when you're an infrastructure guy, you're trying to figure out how many of these guys are going to buy the 2 GB capacity
Mhm.
version versus the four. And what
Sure.
that ended up causing people to do is, it varies over time. Certain parts of the workday, it's going to be more of one kind than another.
Hmm.
And you end up buying really more infrastructure
Hmm.
than you're ever really using at one point in time.
Right.
And that's called the memory stranding problem in the case of memory.
Huh.
And so then the question became, well, how do I minimize the stranding problem? And there have been a couple of really interesting efforts in the industry. One of them is around a new kind of interconnect called CXL. And the
Hmm.
basic idea is, what if on each server, we give you kind of the minimum amount of memory we expect you to use, and then there's this pool that's kind of shared among a bunch of servers
Hmm.
when they get, kind of users that are asking for more memory than they typically would need on one system, they kind of borrow it from this
I
big
see.
pool. And the
Huh.
idea is let's try and minimize the amount of stranded capacity that's there. So, I'd say the industry is very, very aware of this problem. And with memory being so expensive and kind
Huh.
of high consumer of power, the industry starts to think about, these kinds of potential
Yeah.
solutions.
It's like bandwidth on demand. It's memory on demand.
That's right.
You're
Yeah.
metering it. And are there trade-offs to that, right? Is there something to be said for I own this memory or, again, I have to plan for my peak capacity, which means that I'm going to have all sorts of stranded memory, as you say. I'm going to have more than I need for most situations versus getting caught short. But what is the trade-off between that memory on demand, so to speak, or what do you call it again? What is the name
Yeah.
for it?
It was called like pooled memory.
Full memory. Okay.
Yeah. And so, one of the things about having a pool of memory is it's not really right next to the processor anymore. It's kind of in
Hmm.
the middle of a bunch of
I
servers. And
see.
so
I see.
it's a little bit longer latency to get to, and it's a
More
little bit,
power.
yeah, it's more
More
power
power.
to get to as
Yeah.
well. But it's all this trade-off of balancing the cost and trying to reduce the amount of wasted resources.
Hmm.
So there are use cases, and basically it just comes down to a bunch of math. There
Hmm.
are cases where it makes a lot of sense to do this
Hmm.
kind of thing.
So that's where you really need to understand and predict what your workload will be.
That's
and
right.
the type of workload,
That's right.
and maybe it's like peak demand pricing versus off hours, right? You have lower
That's right.
electricity rates at night than you do during the day, during, in the middle of summer, and everybody's looking for it, right?
That's right. In fact, it's a really interesting kind of thing to think through because you are thinking a lot about what your users are doing, and history is a little bit of a kind of an indicator here as well. It's pretty much the case that people that have been over time they're going to gradually use more and more capacity of memory, and so a person who used 2 GB 10 years ago is probably going to be using 3 or 4 now. So you have to be thinking a little bit about what the growth trajectory looks like. You look at the software and you look at the workloads to see what they're requiring as well.
And you get your crystal ball.
Yeah, you get your crystal ball, your magic 8 ball, whatever your favorite
Oh, yeah, and
technique is.
your AI, it's going to give you some answers, right? It's going to make
That's
some
right.
predictions. And so, I would imagine that in some ways it's getting easier to do some of that capacity planning. In other ways, it's getting more difficult and more
Yeah,
complex.
I think the one that's making it really hard right now is the turn towards agentic AI.
Yeah.
So, there's no doubt that it improves productivity. It's a great technology, but the vision is to have, say, a human interact with, one or more agents, and then those agents interact with more agents.
Right.
And so as the number of agents and the number of contexts grows, then what a single user could actually be consuming is much, much higher than what they did in the past. So there's questions about how to make those contexts long-lived. How should they communicate back and forth? And what exactly are they going to do? So that's all an active area right now of
Yeah.
trying to understand how that's going to impact infrastructure.
Well, yeah, and since agentic technology is really so early in its life cycle, that's going to be very interesting. But I can now see how one user could spin up multiple agents, and those agents will be spinning up other agents, and now all of a sudden you're multiplying or by orders of magnitude the capacity that's required in
That's
order
right.
to do this. So that's fascinating. And people think of memory in commodity terms. So what is your, and this is kind of the opportunity to give Rambus a little bit of a plug or a differentiator, not a sales pitch, but what should they look at when they're thinking about memory? And what makes it less of a commodity and what makes it more of a commodity? And then how do you guys position in that marketplace?
Yeah, great question. So I think right now, because the industry is demanding a greater growth rate in the technology than it has in the past, it's really putting the engineers at the forefront that are developing the technologies for the next generations of memory all across the board. So on phones, we're trying to do more inference there. And so we need to go faster and we need to be more power efficient. In your regular computers with DDR, the data rates are going up again faster than they have in the past. And then if you look in the data center, servers, AI engines, and all that, it's all about going, just ultra fast. We're literally at the limits of how fast we can keep pushing based on the manufacturing technology. And so the engineering teams are always trying to squeeze a little bit more out for what really differentiates companies like Rambus. For the last 30 some years, with the companies, with the whole kind of lifetime of the company, about 36 years now, the company's been all about moving data quickly. So we have decades of experience on how to do that and how to do it reliably and at high power efficiency. So with, consuming the least amount of power. All those things are in focus right now. And so for us, it's actually kind of an interesting time because we see across the board a lot of opportunities driven especially by AI.
And so, when you think about Intel doing such a good job of branding the Intel inside, is there a similar Rambus empowered by Rambus, or is there a brand in the market that people would look to and say, yes, I want this kind of technology, or I want to use this firm for the following reasons? Or again, is that kind of under the covers with the hyperscalers? I'm trying to understand where you differentiate, and then how you differentiate, and really what you want people to take away from our discussion about how you can uniquely solve problems or be uniquely positioned.
Yeah, what I would say is maybe we're a little less familiar to the end consumers because the end consumers, if you're buying services from a data center, you don't really think about the memory as much.
Yeah.
But for the people that are building the chips and the systems, we definitely have a good reputation. We're kind of well known in the industry right now. If you're building an AI processor, you will need certain what we call blocks, basically functionality that allows you to talk to memory. And Rambus, we actually sell some of the most important components that allow processors to connect to memory devices. And so I would say kind of in that space for people designing chips or people buying components, memory components and memory modules. We have a nice reputation in the industry for having been around for a long time and producing reliable technologies that are usable across the industry.
That's great. And thank you so much for this interesting, enlightening conversation. Is there anything else that you would like people to kind of walk away with or think about, or other takeaways that you'd like to have them leave with today?
Yeah, I think probably the most interesting thing is this is one of the most exciting times in the semiconductor industry because of all the demand we're seeing. Applications are getting more powerful, which is driving the demand for even better hardware. And so, across the board, and especially in memory, it's an incredibly exciting time. I would say the industry is working really, really hard. We at Rambus are working very hard too to develop new innovations and things like that. We have a whole organization that's looking only towards the future. So we work with our product teams trying to understand the problems, and then we try and innovate ahead of time. And so, I think at Rambus, we've got a lot of interesting work ahead to try and help enable the industry and help kind of keep the flywheel going at advancing AI and other compute. So it's just an incredibly exciting time right now in the industry and for Rambus.
That's great. And is there anything that people should keep in mind if you're who in an enterprise cares about this, and what questions should they ask? So, when you think about decision makers, when they're planning these things, when they're looking at their infrastructure, looking at the compute that they need, what questions should they ask?
I mean, one of the biggest questions is how reliable and how much experience these companies really have in producing these technologies. So I'll give you one example. So when Meta was training Llama 3, they actually wrote a paper and talked about some of the challenges with training it. And it turned out, their infrastructure was going down about, if you work through the numbers, their infrastructure was going down about every 3 hours. Wow. Yeah. And so, it would cause them to take different measures to recover from these kinds of errors. And so the companies you really want to go with are the ones that have a lot of experience and understand reliability. We have 30 plus years of working in those environments, and downtime is a killer. That will really ruin both your productivity and your reputation. So I would say at least for Rambus, I think just that reputation and the experience alone is worth a lot.
And did they attribute those to memory problems?
Yeah, there's actually some that are related to memory. There's some that are related to the processor. They don't go into a lot of detail. Sometimes it's kind of hard to tell exactly what the problem is. And there's a large fraction that are related to memory that they isolated them to. So because it's known that memory and talking to memory can be error prone. Again, you want to go with companies that can demonstrate to you that they have high reliability in doing this.
So asking the questions of the infrastructure provider and the hyperscaler about the types of technologies, what's in the box, what's under the cover is going to be important.
I mean, the worst thing to get are the angry calls from the users when the infrastructure is going down.
For sure.
I mean, that's just not what you want. And so asking the right questions ahead of time can actually reduce those kinds of headaches.
Gotcha. Well, Stephen, this has been great. I really appreciate your time. Thank you very much for joining us today. And I think it's, again, it's one of those things that you don't really think a lot about, or at least people like me don't think about, but it's part of that key and that core infrastructure that enables all of these incredible things to be taking place.
I enjoyed our conversation today, Seth. Thank you very much.
And thank you to our audience. Appreciate you guys tuning in, and we will see you next time at the next Early AI podcast.
Thank you for joining us on another deep dive into AI innovation. Tune in next time when we introduce another industry expert and discuss how to maximize AI in your world. The Early AI podcast is sponsored by Early Information Science and Vector. To learn more, visit early.com. That's EARLEY.com. Thank you for tuning in.